I am Dr. S. Sundaram, former head of the Department of Chemical Engineering in NIT Trichy. I am going to give a series of lectures on chemical engineering thermodynamics. Okay, I'll start with the first chapter, introductory chapter on thermodynamics. So, thermodynamics, the name means transfer of heat, okay, motion of heat. Okay, more precisely, it is the motion of heat. The motion of heat. However, this subject was framed nearly a century ago, wherein the only form of energy transfer was thermal energy to mechanical energy. James Watt is the engine. Okay. Subsequently, over the years, number of with different types of energy transfer is possible. For example, chemical energy to electrical energy in battery. Okay. Then hydropower energy, hydroelectric energy to electrical energy, potential energy to electrical energy, and so on. Now, let's try to see what I can do. In thermodynamics, we learn thermodynamics with four laws. First law, second law, third law, and fourth law. The first law is based on energy transformation. One form of energy is being transferred to another. So it talks about energy transformation. Second law says direction of the process. Which is possible? Is it possible or not? For example, if A plus B gives C plus D, will A plus B give C plus D or C plus D give A plus B? So what is possible? What is the direction of the process? The third law deals with the one absolute property called entropy. See, entropy is absolute property. What is an absolute property? Any property which has got zero value. For example, volume has got zero value. Now, if any property is zero value, is got an absolute property. So, I've told you with first law, second law, and third law. There's one more law called zeroth law, which talks about equilibrium. Okay, suppose there are three objects A, B, and C. If A and B are at equilibrium, B and C are at equilibrium, therefore A and C will be equilibrium. That's the zeroth law. So we got zeroth law, first law, second law, and third law. Now I am going to deal with SI units. SI units, System International Units, where mass is in kg, length in meters, time in seconds, okay, and temperature, degree Kelvin, work in Newton meter, force is Newton, okay, force in Newton, energy, Newton meter or joule, because we know 1 Newton meter is equal to 1 joule, okay, and power is joules per second. So these are the units that we are going to use. Mass is kg, length is meters, time in seconds, temperature degree Kelvin, work in Newton meters, etc. So these are the basic things you are going to follow. Now, before I go further, let me give some brief introduction to various parameters we used in thermodynamics. Now, first is called system and surroundings. System and surroundings. System is defined as definite quantity of matter. Definite quantity of matter or confined region of space. Confined region of space. Everything outside this system is called surroundings. For example, suppose I am focusing on my stomach. Stomach is my system. Okay, my other parts of the body are my surroundings. Similarly, if you take a piston and cylinder arrangement, gas is here. This is a piston. This is a cylinder. Now, if you take gas as a system, then cylinder, piston becomes surroundings. Okay, and the atmosphere also surroundings. So gas is a system, cylinder, piston, and the atmosphere is surroundings. Suppose I take the gas plus cylinder plus piston as my system, then the surrounding all over becomes the surroundings. Other things will be So we got system is gas, piston, cylinder. Other thing outside is called surrounding. So depending on what you choose a system, you got system and surrounding. Normally, how do you choose a system? Suppose I want to focus on something. That has always taken a system. Everything outside the system is called surroundings. Now, system is defined as the three types: closed system, open system, and isolated system. Now, if we take open system, both energy and mass transfer is possible. If we take closed system, energy transfer is possible. Energy transfer is possible. Mass transfer not possible. If we take isolated system, both energy and mass transfer not possible. So let me once again define. Open system is one with both mass and energy transfer is possible. In a closed system, energy transfer is possible, mass transfer is not possible. Isolated system, both energy and mass transfer are not possible. So this is the basic definition of a system and surroundings. As and when you proceed, I'll try to explain more and more about this system and surroundings. Now, what is work and energy? Work and energy. Energy is capacity to do work. The capacity to do work. And work is defined as energy in transit. For example, if I have to remove this duster from this point to this point, what I am doing, I have to do work. Okay? What happens in this process? At this point has got certain potential energy. At this point has got other potential energy. Therefore, I want to change the potential energy from this to this. That is, if I want to transfer energy from one level to another level, I require work. That's why work is called energy in transit. Transit means transferring something. Okay? Work is called energy in transit. Now, here again, energy has got number of classifications. We take energy. We've got microscopic energy, and macroscopic energy. Microscopic means you can't see with the naked eye. You can see only through a microscope. Macroscopic can be seen in the naked eye. For example, the molecular movement. For example, according to kinetic theory of gases, the gas molecules can move about. That means they have got kinetic energy. Okay, so this molecule movement, you have got kinetic energy. They got oscillatory energy. They can oscillate. Therefore, it's called oscillatory energy, vibration energy, oscillatory energy, rotational energy. It's called rotational energy and vibration energy. That is, the molecules can move up and down like this, fast. Therefore, it's called kinetic energy. The molecules can rotate like this. That's called rotational energy. They can vibrate. At a very high temperature, they can vibrate. It's called vibration energy. So, microscopic energy is divided into molecular kinetic energy, rotational energy, and vibration energy. Whereas macroscopic energy can be seen with the naked eye. Suppose a car is moving. It has got a velocity. It has got a mass. So, mv square by 2, that's the kinetic energy of the car. Okay, water stored in an overhead tank has got potential energy. You can see with the naked eye. So these two are called macroscopic energy. Now, one more thing I'm going to define is state function, also called point function and path function. State function or a point function. Suppose you got your house is here, your shop is here. Okay, house. Now I can go from the house to the shop like this, or I can take a path like this and go like this, or I can go like this. Anyway, I got from 1 to 2, I got one path, two paths, second path. Now, irrespective of the path I take, the position of the house and shop are fixed. It doesn't change, it's always there. That means that which does not change with path is called a point function or state function. Okay, so the position of the house and the position of the shop are called state functions or point functions. On the other hand, if I go and take this route, if I'm walking or if I'm going a bike, the petrol consumed is more, the mileage covered is more. So the mileage and petrol consumptions are called path functions. So it depends on the path. If you go by this path, mileage will be lesser and petrol consumption will be lesser. If you go by this path, mileage will be more, petrol consumption more. So anything which is depending on the path is called a path function. Anything that does not depend on the path is called point function. Now mathematically, if Z is a function of x and y, for example, we know V equal to RT by P for ideal gas. So V is a function of temperature and pressure. Okay. Now, if dou square Z by dou x dou y is equal to dou square Z by dou y dou x, then it's a point function. So for a point, if Z is a point function, then it should satisfy this condition. Dou square Z by dou x dou y is equal to dou square Z dou y dou x. If dou square Z by dou x dou y is not equal to dou square Z by dou y dou x, then it's a path function. So this is state function, this is a path function. Now we can show that the volume of ideal gas is a state function. Okay, we will apply this formula and show that volume of ideal gas is a state function. Show V is a state function. For example, V is a function of temperature and pressure. Now we can show that dou square V by dou T dou P equal to minus R by P square. Similarly, dou square V by dou P dou T is also equal to minus R by P square. You can try the differentiation and try out. You will see that. So in both cases, we get minus R by P square. So that means dou square by dou T dou P is equal to dou square V by dou P. What does this dou square by dou T dou P mean? First you differentiate V with respect to T, keeping P constant, and the second differentiation with respect to P, keeping temperature constant. Here, if first you differentiate with respect to P, keeping T constant, and second differentiate with respect to temperature, keeping P constant. So this is a state function. So state function is there. Some more properties of state function I will tell you. Some more properties of state function. If you take a state function, the cyclic integral of state function is 0, whereas cyclic integral of path function is not equal to 0. That means what does physically mean is, suppose I start from this point and come back to this point. Okay, so if I come back to this point, now for a state function, when I go like this and come back here, the change is equal to delta means change equal to 0 for a state function. Whereas for a path function, delta is not equal to 0 for a path function. Now with this, we'll continue next class and we'll go for other things on thermodynamics. We'll take up the first law of thermodynamics next class. Thank you.